Hello students, welcome back to the classroom point. In our previous class, we had discussed the colligative properties in that related lowering of vapor pressure. So in our today's class, let us discuss the remaining colligative properties, that is elevation of boiling point. So let's begin the class. Elevation in boiling point of solvent. So it is denoted by delta TB. So let us see how the boiling point of a solvent and a solution or a compound, how it will be defined. So let us take a solvent in a beaker, in an open beaker. Even at normal temperature, solvent molecules, even at room temperature 25 degrees centigrade, there is some vaporization takes place. So some of the liquid molecules go to the vapor state, gaseous state, and form the vapor. But in the open beaker, the pressure of the atmosphere is equals to 1 atmosphere. This is equals to 1.013 bar pressure in terms of the pressure bars. So solvent molecules do not get the sufficient energy to create the vapor whose pressure is equals to atmospheric pressure. Then if you want to make this solvent to boil, we need to heat it. So when temperature rises, vaporization rises, so that more vapor will be formed, and this vapor obviously exerts the pressure. That vapor pressure can be called as the pure solvent vapor pressure. So this vapor pressure, whenever it is equals atmospheric pressure, so that temperature is known as the boiling point. So the temperature at which the vapor pressure of a solvent is equals to atmospheric pressure is known as the boiling point of the solvent. So let us take the solvent here, water. So water boiling point, we know that 100 degrees centigrade, normal boiling point of the water. That means at 100 degrees centigrade, the vapor pressure of the water is equals to atmospheric pressure. So that P naught of water is equals to 1 atmosphere, or else we can take this 760 millimeters of mercury. Now here the concept is about the elevation. That means increase in the boiling point. So how the boiling point of the solvent is increased? Let us try to add some amount of the non-volatile solute. So I am taking the 1 gram of non-volatile solute. So as the condition it is non-volatile, so that the solute molecules do not participate in the vaporization process. But here in a homogeneous solution, this non-volatile solute completely and uniformly distributes throughout the volume of the solvent, so that the solute molecules not only occupy the positions in the bulk of the solvent, but also replaces the sum of the solvent molecules from the surface area. So during the vaporization, only solvent molecules participates, and where the solute molecules are occupying the surface area. So whenever the vaporization process decreases, because solvent molecules decrease, automatically vaporization decreases, vapor pressure also decreases. That vapor pressure is known as the vapor pressure of the solution. Now between pure solvent vapor pressure and the solution vapor pressure, the vapor pressure of the solvent is more than the solution vapor pressure, because in case of the solution, vaporization decreases, number of vapor molecules decrease, pressure also decreases. So imagine the pressure of the solution is equals to 700 millimeters of mercury. Then now Actually, this water boils at 100 degrees centigrade. That means at 100 degrees centigrade, its pressure is equals to 760. But now its pressure is equals to, even at 100 degrees centigrade, 700 millimeters of mercury. That means this is not sufficient to equalize the 1 atmospheric pressure. So to create the vapor pressure is equals to atmospheric pressure for this solution, we need to raise the temperature beyond 100 degrees centigrade. Then its pressure starts increasing and become equal to the 1 atmospheric pressure. Then the solution starts boiling. That means indirectly the solvent boiling point is raised by adding the some amount of the non-volatile solute. Now, instead of the 1 gram, what happens if the 2 grams of non-volatile solute is added? So when the quantity of the solute increase, automatically number of solute molecules from the number of solvent molecules from the surface area replaced by the solute molecules. So still vaporization drops, vapor pressure also drops, so that the temperature required to create the pressure increases. That means when the quantity of the solute increases, we say that concentration of solution increases. When concentration of solution increases, vaporization decreases, vapor pressure decreases. So that we need to give the higher temperatures to create the vapor pressure whose pressure is equals to atmospheric pressure. So indirectly the boiling point of the solvent is increased by adding the non-volatile solute. Higher the amount of the solute you are adding, more shall be the boiling point. So that when the concentration of solution increase, boiling point of the solution also increase. So let us take a graph that gives the picture between the vapor pressure and temperature. Temperature we are taking the x-axis and the vapor pressure on the y-axis. So this is the dotted line that represents the 1 atmosphere, that is the atmospheric pressure. Now imagine there is a solvent. So the solvent is at here at a particular temperature. When you are raising the temperature, the vaporization and vapor pressure of the solvent increase. After a certain time, its vapor pressure is equals to atmospheric pressure. So from here it starts boiling. So that is what called the boiling point of the solvent. It is represented by the letter T naught B. This is solvent. Let us take the solution with 1 gram. So solution vapor pressure obviously less, so that it begins from the bottom of the solvent curve. Again, when temperature increase, vapor pressure increase. After certain period of the time, its vapor pressure is equals to atmospheric pressure. So from here it starts boiling. That is the boiling point of the solution. So I am taking this solution as 1. So that here I am taking this boiling point of the solution 1. Next, 2 grams of the solute when added, so that the concentration increase. So obviously its evaporation decrease, so that again when temperature increase, its vapor pressure increase. Finally it reaches a certain point where it starts boiling, so that I am taking the vapor pressure of the solution 2. Solution 2. So from here to here concentration increases. You can see this is the difference in the vapor pressure, that is lowering of vapor pressure, and this is the lowering of vapor pressure for the between the solvent and solution 2. When the concentration increases, the difference of the vapor pressures, that is lowering of vapor pressure, also increase. So we can write down that lowering of vapor pressure is directly proportional to the concentration of the solution. Now here this is the vapor boiling point of the solvent, this is the vapor boiling point of the solution 1, this is solution 2. So from here to here it is called the difference in boiling point, and from here to here this is called the difference in boiling point. So from here to here boiling point of the solvent increase. So this boiling point of this solvent is nothing but the delta TB. That is delta TB represents the enhancement in the boiling point of the solvent. That is what called the elevation of the boiling point of the solvent. So here when concentration of the solution increase, boiling point differences also increase. So that we can say that delta TB, that is elevation of boiling point of the solvent, is also directly proportional to the concentration. But how to calculate the elevation of boiling point? Always a solution boiling points more than the solvent boiling point. So that we can write down that TB is always greater than the T naught B. When concentration increases, boiling point value also increases. So when you want to calculate the delta TB value, we have to subtract the lower value from the higher value. Here higher value is boiling point of the solution, lower value is boiling point of the solvent. So delta TB equals to TB minus T naught B. As I said here, delta TB is directly proportional to the concentration. So that concentration I am taking as molality. The reason for taking the molality is independent of the temperature, because this condition is here we are changing the temperatures. So if you take the molarity at normality, when temperature changes, first concentration also changes along with the vapor pressure, then we have to consider the three parameters. It becomes difficult for us. If we take the molality do not change with the change of the temperature, so that we can easily calculate the relation between the temperature as well as the vapor pressure. So that now here delta TB is equals to, let us try to replace this proportional symbol using the constant, that is KB into M. So what is M? M stands for the molality. So that here we can write down that delta TB equals to KB into molality. Formula is weight of solute divided by molecular weight of solute into 1000 by weight of the solvent in grams. So let's define about the KB. So what is KB now? KB is also known as boiling point elevation constant or else molal elevation constant or ebullioscopic constant. Then how to calculate the units and the KB values? Let us see here. KB is equals to, you can send the molality this side, so that it becomes the delta TB divided by molality. Delta TB means TB minus T naught B. Temperature minus temperature, again gives the temperature only. So that units of the delta TB equals to kelvins. And here the units are molality, so that we can write down the molality power minus 1, or else kelvins kg per mole are the units of ebullioscopic constant. Then how to calculate the KB value? So KB value is equals to R T naught B square divided by 1000 L V. V stands for the latent heat of vaporization, and R stands for the universal gas constant. T naught B stands for the boiling point of the solvent. Then latent heat of vaporization. So how to calculate means delta H vaporization is equals to molecular weight of solvent into latent heat of evaporation. So that latent heat of evaporation equals to delta H evaporation divided by molecular weight of solvent. So by substituting its value in this equation, so we shall get it KB is equals to R T naught B square divided by 1000 into molecular weight of solvent divided by delta H of vaporization. Now KB value, you see that these are all constant values for a mole of the substance. Delta H evaporation for a mole of the substance, a particular substance constant, R value constant, boiling point of this particular solvent is constant, 1000 is constant. So KB value depends on solvent. If the nature of the solvent changes, its molecular mass also changes. So here we can write down that KB depends on solvent, and for Kb for water is equals to 0.52 kelvins kg per mole. So from this it is very clear that when the concentration of the solutions increase, automatically boiling point value also increase. If you take 1 m of urea solution and 2 m of urea solution and 3 m of urea solution, so the boiling point order is 3 m of urea solution is having the higher boiling point than the 2 m urea solution. 2 m is more than the 1 m urea solution. When concentration increase, boiling point also increases. Now let us take the 0.1 m urea solution, 0.1 m NaCl solution, 0.1 m BaCl2 solution. As this is elevation of boiling point is a colligative property, depends on the number of solute particles. So here urea can produce only one solute particle. So 1 into 0.1 means particle concentration is 0.1. In this case, NaCl can produce the two ions, Na plus Cl minus ions. So number of ions into concentration gives the particle concentration. So 0.1 into 2 equals to 0.2. Here BaCl2 can produce 3 ions, one Ba2 plus ion, 2 Cl minus ions. So given concentration 0.1 into 3 equals to 0.3. Wherever higher particle concentration is there, then automatically boiling point value is also higher. So here 0.1 m BaCl2 has the higher boiling point than the 0.1 m NaCl, and which is having the higher boiling point than the 0.1 m urea solution. So this is about the elevation in the boiling point.